A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about elasticity, which is a starting point for the discussion on constitutive models. So let's get started. So an elastic material is a material where the stress only depends on the current strain, that is, it does not depend on the history of loading and is a completely reversible process. So the model is represented as the response sigma written as a function, a tensorial function of the strain epsilon KL, where epsilon is the symmetric part of the displacement gradient tensor. So basically, in elastic materials, what happens is that whatever mechanical work is done during the loading, that is completely stored as strain energy, and it is fully recoverable upon unloading the material. So it is a reversible process. And as we'll be discussing later, the quantities are state functions. They're not path functions in elasticity. And that is what is used to represent a fully reversible situation in elastic solids. In contrast, we have viscoelastic materials and plastic materials where the stress depends on the history of loading. So in viscoelastic materials, as we discussed last time, we have to use kernels or internal variables to represent the history dependence. And in plastic materials, which are actually irreversible processes, a residual plastic strain remains upon unloading the material. So two key features of elastic materials are that they depend on the instantaneous strain, that is, not on the history, and it's a fully reversible process. Under elastic materials, we have linear elastic materials. So that is what is called the theory of linear elasticity. So we always start our discussion with linear elasticity because mathematically that's the easiest theory to develop. And practically speaking, we can approximate solids or their behavior as linear elasticity sometimes for narrow range of strains. So the constitutive law in this case of linear elasticity is that sigma is written as the constitutive tensorCijkl times epsilon KL. This constitutive tensor C is a fourth order tensor that allows us to map the strains to the stresses, and in 3 dimensions it will have a maximum of 81 components in principle. So if I look at this relationship, then what I see is that a sigma, let's say sigma 1, 2, would be written as a linear combination of the different epsilons. It will be some value or coefficient times epsilon 1, 1 plus some coefficient times epsilon 1, 2 and so on. So it's a linear combination of the different epsilons that results in a given sigma. So every sigma is a linear combination of different epsilons, and that is what results in this linear map for the linear elastic material. Now, although we say that our constitutive tensorCijkl has a maximum of 81 components, but because of the symmetry of stress and the symmetry of strain, we can reduce the number of components of C from 81 to 36. So let us do that derivation rigorously to see how we can get from 81 to 36 components because of the symmetry of stress and strain tensors. So sigma ij is written asCijkl times epsilon KL. Now if sigma is symmetric, that is for sigma ij equal to sigma ji, this will imply thatCijkl is Cjikl. So let's see this term by term. So let us say we're talking about C12 KL is C21 KL. So C21 KL for all values of K and L will be a total of 9 components. Now since we are saying that C12 KL is C21 KL, so for all these 9 components which are coming from C21 KL, they are redundant, so we can get rid of those because they're already present in the tensor in the form of C12KL. So I say this results in a minus 9 components in the tensor. And similarly, because we have condition C13KL is C31KL, that again results in a minus 9, and then C23KL is C32KL, so that also results in a minus 9. So overall, we have a minus 27 here because of the symmetry of the stress tensor. Now let us look at the case where the strain tensor is symmetric. So since epsilon KL is epsilon LK, so this will imply that Cij KL is Cij LK. Now with the same brute force logic, we can see that Cij 1 2 is Cij 2 1. So that should result in a minus 9 components like last time. But if you look at this one, this may have components like C2121, C3121, and C3221. Now these components we already had discounted here. Like from here, C21KL, we discounted all the components, all the 9 components. So C2121 is also one of those. So basically what we see is that since we already have discounted these 3, so effectively we are left with minus 6 components because of the symmetry of the strain tensor. So by that logic, we have a total of, again, minus 6 times 3, that's a minus 18 components. So if I take this minus 27 and minus 18, then overall we have 81 minus 27 minus 18, that is 36 components left. So we have shown that because of the symmetry of the stress and the strain tensors, we are left with 36 components rather than the 81 that we started with. So when I say we are left with 36, that means we are left with 36 unique components. Of course, the other components will be there. It is just that we don't have to use a separate storage space or another variable to store them. Now next we'll see that we can actually further reduce the components from 36 to 21. And this reduction is based on major symmetry. So what we did earlier is actually called minor symmetry. So the idea of major symmetry is based on the fact that there exists a work function or a work potential or a scalar potential W, which is a function of epsilon, which for this case is a quadratic potential. And this results in the symmetry thatCijkl is CKLij, which results in a further reduction. So let us see how that happens. So our sigma is written asCijkl times epsilon KL for a linear elastic material. Now let's recall the idea from mechanics that for a conservative force or a conservative force field that is path independent, we can define a potential energy function. And that's a very interesting idea because that allows us to write the force field, which is basically 3 scalar fields in 3D, as the gradient of a single scalar function u. So we use the same idea in elastic materials which are reversible. So we say that we can define sigma ij as del by del epsilon ij of a scalar potential W, which is called the work function. Or it is also popularly known as the strain energy. So we say that stress or the stress tensor is work conjugate to strain. You may also relate this from the restrictions from thermodynamic principles, where we said that sigma ij is rho times the partial derivative of the Helmholtz free energy with respect to strains. So the idea is very connected, and we'll discuss that soon. So now with the idea of this W, or the scalar potential, so for a linear elastic material, if I take the derivative of sigma with respect to epsilon KL, what I get isCijkl, which can be written as del 2W by del epsilon ij times del epsilon KL. So we have used the idea that sigma ij is del by del epsilon ij of the scalar potential W. Now, although I've written this relationship for a linear elastic material, this relationship is more general. So without showing that, we will be using this for non-linear elastic materials as well later. From this relationship now, I can see thatCijkl is the same as CKLij because of these terms here that result in the symmetry. So this third condition should help us to go from 36 to 21 components or unique components in the tensorCijkl. Actually, to do that, we use a very neat trick, and that is the trick where we use something called the Voigt notation. Now, with this linear elastic material, what we noticed was that sigma is linearly related to epsilon. That is, the components of sigma are linear combination of the components of epsilon. And since I only have 6 unique components of sigma because of its symmetry, and 6 unique components of epsilon again because of its symmetry, I can define a new notation called a Voigt notation, where I say that sigma 1 is called sigma 1. I'm defining a sigma with a single index, then sigma 2 is a sigma 2, and so on. And we can do the same thing for epsilon as well. Then what we see is that our sigmas in the Voigt notation now are still a linear combination of epsilons in the Voigt notation. So whatever the coefficients of these epsilons are, we will call them C tildes, and since we have a 6 by 1 matrix here and a 6 by 1 matrix here, so this is going to be a 6 by 6 matrix here. So this C tilde is a 6 by 6 matrix which has 36 components written as C tilde 1, C tilde 1, and so on. So this is called Voigt mapping. So basically from here we can very easily see that this C tilde has 36 components. So whatever we did earlier to show from 81 to 36 is already visible here from the symmetry of epsilon and sigma. But please remember that C tilde is not a tensor. It does not transform like a tensor. The actual tensor isCijkl. Because sigma is not a vector with 6 dimensions, sigma is a 3D tensor. So this work is purely for notational representation. It has nothing to do with the actual tensorial quantities. So C tilde is not a tensor. Right, so when we said sigma ij isCijkl times epsilon kl, and now we are saying sigma alpha is C tilde alpha beta times epsilon beta, just purely in the matrix notation, we can see that this ij is corresponding to alpha and KL is corresponding to beta. So the symmetry condition, which wasCijkl is CKLij, basically becomes C tilde alpha beta is C tilde beta alpha. That means C tilde as a matrix is symmetric. So if C tilde is symmetric, that means its 15 off diagonal terms can be removed. Again, when I say removed, I mean it's redundant. So we have a total of 36 minus 15, which is equal to 21 unique components left in ourCijkl. So finally, we have shown that because of the minor symmetry, that is symmetry of sigma and epsilon, we get to 36, and because of the major symmetry, that is because of the existence of a work potential, we get a total of 21 unique components left in the fourth order tensorCijkl. Now these 21 components that we have gotten are for a general tensor. But if for a very special case, our material is isotropic, then we see that our sigma has this form which only has two constants, lambda and mu. So as a part of a tutorial problem later, we will be deriving this expression for sigma as a function of epsilon for isotropic materials. But let's discuss this expression today. So this lambda and mu, they are called Lamé constants, where mu actually is the shear modulus as we understand from strength of materials ideas. But what we can notice here is that from those 21 components, we simply go down to 2 for an isotropic material. So this 21 actually is for a general anisotropic material. Of course, if the material has certain special symmetries or certain special type of anisotropies, the number of components may be somewhere between 21 and 2. And this isotropic linear elastic law that we have here between sigma and epsilon, it boils down or reduces to sigma equals E times epsilon for a uniaxial loading, and which is our familiar Hooke's law. In linear elasticity, we have different measurable constants such as Young's modulus, Poisson ratio, the shear modulus, the bulk modulus, and we just saw these two Lamé constants, lambda and mu. So using any two of these, all others can be obtained using these relations. So now that we've talked about the relationship between sigma and epsilon, let's look at an energy viewpoint for this same linear elasticity that we've been discussing. Now we already stated that for linear elastic materials or elastic materials in general, there exists a potential, or more properly, a strain energy density. Now this energy density function W exists or may exist for a general elastic material, but for a linear elastic material that is also isotropic, I should mention isotropic, it takes this special form which is quadratic in nature because you have product of epsilons in the terms. And as we have seen that sigma and W are related like this, so if you take this energy density function and take the derivatives, you get this form which is exactly the same as we saw in the previous slide. So for a general elastic material, we can define a strain energy function because of the reversibility of the phenomena. But for linear elastic material, this function takes a quadratic form, and for isotropic linear elastic material, it takes this form that we see here specifically. So now that we have a good understanding of linear elastic materials, let's go more general. Let's talk about non-linear elastic material. And we'll be talking particularly about hyperelastic material. So let's understand what all these terms mean. So nonlinear elasticity is the general situation where you have a finite strain setting. So for finite strains, you'll expect that there'll be nonlinear effects which become prominent. But out of all these nonlinear elastic materials, hyperelastic materials are those nonlinear elastic materials for which we can define a strain energy function W. So nonlinear elastic materials can be hyperelastic, where a W exists, and others are the ones which are nonlinear elastic, but a W does not exist. So we are focusing on this branch where a strain energy potential W exists. Now, as we know that for finite strain settings, we tend to use the measure C because it is objective. So we define our finite stress tensor, that is the Piola-Kirchhoff 2 stress tensor, as del W by del CAB. And there's a factor of 2 as well. And the Cauchy stress tensor sigma is related to the Piola-Kirchhoff 2 stress tensor, like this, as we have seen earlier. So the general recipe of hyperelastic materials is that you write your stress as a derivative of the energy density function. Now briefly I mentioned earlier that our strain energy function W and the Helmholtz free energy are related. So let us see how. So the free energy, or the Helmholtz free energy, is defined as the internal energy E minus T times entropy. And let us say our Helmholtz free energy is written in a very general sense. So it's a function of epsilons, T, and internal variables alphas. Now for a purely elastic isothermal material, our free energy would only be a function of epsilon, and that actually becomes the same as the strain energy W. So what we are saying is that for elastic isothermal settings, our strain energy W is the same as the Helmholtz free energy psi. They are the same thing. But for other cases like thermoelastic materials or viscoelastic or plastic materials, we see that the Helmholtz free energy is not the same as the strain energy density function W. So they are not always the same. And let us say for thermoelasticity, our psi is a function of epsilon and T. So the mechanical work that is done is not purely stored as strain energy. It alters both the strain energy and the thermal state. Although the changes are still reversible, that is, there's no dissipation, but still our free energy is not the same as strain energy, because free energy is something more than W. Now for viscoelastic or plastic situations, in the second case here, they are actually irreversible processes. So our psi, which in this case also has internal variables because of the history of the loading condition, we see that some work is stored, but the other work is lost as heat. So in this case, definitely the free energy cannot be the same as W. So in general, we cannot say that psi and W are the same, but for our purely elastic and isothermal situations, indeed the free energy psi and the strain energy W are the same. So basically we can say that the choice of this strain energy function W is not an ad hoc mathematical trick that we are applying here. It is actually coming from the principles of thermodynamics. Now for these hyperelastic materials, that is nonlinear elastic materials for which a W exists, let's talk about isotropic hyperelastic materials. So when these hyperelastic materials become isotropic, then we write our W in terms of the invariants of C. So what we'll do now is that we'll talk about a particular hyperelastic model, the most basic one, that's called a Neo-Hookean model. Neo-Hookean models are the simplest isotropic hyperelastic models which are widely used for materials such as rubbers, polymers, and soft tissues. Since the general way of doing things in elasticity, as we are seeing now, is to write things in terms of the strain energy density function W. So we develop this function first, and from this function we get our finite stresses at pk2 by using this relation. So this is the form of our finite stress tensor that we get for this situation, and we can also get the Cauchy stress using the relation between pk2 and the Cauchy stress tensor sigma. So if you look at this function, we have a term which takes care of the shear in the material, and we have these two terms which take care of volumetric expansion or compression. So let's analyze this a little further. So for this Neo-Hookean material, that is our isotropic hyperelastic material of choice, we just showed that the Cauchy stress tensor sigma is written like this, where B is basically F times F transpose. So let us apply an incompressible limit on the material, that is the Jacobian is equal to 1. Now we cannot naively substitute j equal to 1 here, because that will give us sigma is mu times Bij minus delta, and that will result in the loss of the hydrostatic part. So basically incompressibility is when lambda tends to infinity and j tends to 1. So if you look at this term here, when lambda tends to infinity and j tends to 1, this is infinity times 0 form. So this should tend to a constant, and that constant times delta Ej, and this mu times minus delta Ej can be combined into a minus P, which is called hydrostatic pressure. So we get this form of sigma. So this is the form for the Cauchy stress tensor for an incompressible Neo-Hookean material. So it's incompressible, and Neo-Hookean materials are isotropic, hyperelastic. And basically hyperelastic is nonlinear. So this is for finite strain situations. And that is the reason we are using this B, that is F times F transpose, as a measure to write the constitutive model. So small strain limit is where our F is given like this, C approximates to this, and J approximates to 1 plus the trace of epsilon when approximating up to the first order. That's very important. And when we substitute these small strain approximations into our Cauchy stress tensor expression for Neo-Hookean materials, what we see is that this expression boils down to the same isotropic linear elastic expression with the two Lamé constants lambda and mu. So our isotropic nonlinear elastic model under small strain limit boils down to the isotropic linear elastic model as we see here. So we talked about linear elastic materials where we see metals, ceramics, and in general small deformation situations for many materials. And then we talked about hyperelastic materials, which are typically used for rubbers, polymers, and soft tissues for large strains or finite deformations. And then we also have a class called thermoelastic materials, where our sigma depends on epsilon and the delta T. So delta T is basically the temperature difference between T and T naught, where T naught is some stress-free temperature where there's no stress. So the idea of today's discussion was to give you an understanding of these elastic models which are used to model many solids. But still we have some limitations because these elastic models do not cover viscoelastic situations where there is a rate effect, that is, it depends on how fast the strain is changing. It cannot model plastic materials because there's no irreversible situation discussed. We always talked about a reversible situation for which a W existed, and it still cannot model damage or failure as well because that requires additional ingredients. Here's a quick concept check. That is, for linear elasticity in 3D, how many independent components does our fourth order constitutive tensor require? In first, if you only apply minor symmetries, and second, if you apply major symmetries as well. So let us summarize today's lecture. So today we talked about elasticity or elastic solid. And elasticity can be linear or non-linear. In non-linear, we can have either hyperelastic materials or other materials which are not hyperelastic. And again, in linear, we can have isotropic or anisotropic materials. Similarly, hyperelastic, we can have isotropic and anisotropic. Now, what differentiates linear and nonlinear is that for finite strain situations, we tend to use nonlinear models. But for small strain situations, a nonlinear model will boil down to a linear model, which is what we saw when we discussed the Neo-Hookean material, which was isotropic hyperelastic material, and we applied the small strain situation for it. So this boiled down to the same linear isotropic constitutive model. So we started today's lecture with linear elasticity, where we said our sigma and epsilon are related through this CIJKL with 21 unique constants. Then we applied the idea of isotropy to get the two Lamé constants lambda and mu. Then we generalized our idea of the strain energy density function W, which was then used to define the finite stress tensor, that's Euler-Kirchhoff's 2 stress tensor for hyperelastic materials, which was followed by a discussion on isotropic hyperelastic materials. And then we finally closed the loop by showing or checking that our model for isotropic hyperelastic material, that's a Neo-Hookean material, boiled down to isotropic linear elastic material for small strain limit. Now, although the discussion on linear elastic material was meant for solids, but the ideas that we developed will be applicable to linear fluids as well. So in the next lecture, we will talk about viscous models where stress is related generally to the rate of strain epsilon dot. So thank you very much, and I will see you in the next lecture.